the Spring 2010 Ann B. Shepard Lecture Series, Modern Marvels, Engineering the Future. When the lecture committee comes up with an idea for a series, we often, in fact, almost always, try to find someone at the university who can help us structure our ideas, tell us whom we should ask to speak, and in general help us turn our good idea into a coherent series of lectures. The adult school board member who came up with the idea for this term's series was Cy Marchand, and the person we turned to for help was Vincent Poor, the dean of Princeton's renowned School of Engineering. Dean Poor was extraordinarily generous with his time and help, and it occurred to us that since he had been so nice, we should impose on him even more, and we would ask him to introduce the series, to share his excitement and enthusiasm about the kinds of things the School of Engineering is doing that will be reflected in the talks we'll be hearing over the next several weeks. So you're getting a twofer tonight. Dean Poor will give us an overview, and then I will introduce tonight's speaker, and then we'll have our lecture. If you like the idea of this series, here's the person to thank, Dean Poor.
Thank you, Nancy. Good evening. Can you hear me? Yeah, okay. I have a pretty loud voice. First of all, I'd like to thank Nancy and her colleagues at the Princeton Adult School for choosing engineering as the focus of this spring's lecture series. I've been to many of these lectures over the years, and I even gave a talk in one of the series a few years ago, and I'm really happy to see engineering in the highlight this time. It's particularly appropriate since we're in one of the engineering buildings here. Nancy asked me to say a few words about the engineering school as a way of introducing this series, and I'm very happy to have the opportunity to do so. Mindful, though, that all of you came to hear Emily Carter tonight. I'll try to be brief, so I won't take too much of her time. Let me begin by noting that engineering at Princeton, the engineering school at Princeton is a fairly large part of Princeton University. We have about a fifth of the undergraduates, a quarter of the graduate students, and about a third of the research expenditures go through the engineering school. So there's no way that I could, in this short time, do justice to all the things that are going on. But I thought I'd try to give you just a sense of what we do and to put this series in that context. And to do that, I think it's helpful to start with a question, which is, what is engineering? It seems like a very simple question, but I think the answer to it will help frame this series and also more generally what we're doing here in the engineering school. It's not particularly an easy question to answer. I think most people might stumble on the answer to that question. But I think it is simple to answer a related question, which is, what is science? Science is basically the study of the natural world. So scientists are people who seek to explain nature. Now, in the academic enterprise, we have the so-called two cultures, science on the one hand and the humanities on the other hand. And the humanities, and I should include the social sciences in this, are about trying to understand human beings, either as individuals in the humanities or collectively in the social sciences. So we have on one hand a group of intellectuals and others trying to understand nature. On the other hand, a group of intellectuals and others trying to understand human beings. So where does engineering come into this? Well, engineering is about using scientific knowledge to do things, useful things for society. So engineering is somewhat of a bridge between the two cultures of science and humanities. And that's true in the academic world, and it's also true in a slightly more general context in the real world as well. Now, of course, this is a gross oversimplification. The lines between science, engineering, humanities, social sciences are quite blurred. Many scientists are interested in applications. Many engineers are interested in understanding the natural world and so forth. But I think it's philosophically, I think it helps define what engineering is, and particularly how it fits into an institution like Princeton. So a good example of this arises in the subject of tonight's talk, and actually of several of the talks in this series, and that is energy. Scientists, particularly geoscientists in this case, will tell us that if we continue to burn fossil fuels at the rate that we are to produce energy, we'll ruin our environment. On the other hand, social scientists, in this case economists, will tell us that if we don't produce energy at the rate we're producing energy, we'll ruin our economy. So we have on the one hand a scientific fact, and on the other hand a social need, and there's a gap between them. So this is where engineering comes in. Engineers can develop new technologies that will help us create energy, produce energy in a sustainable way so that we can run our economy without wrecking our environment. And this is just an example of many such problems where there's a conflict between scientific fact and social need, and technology often fills that conflict. If you look at many of the debates that we have, the national debates and international debates we have today, many of them have this characteristic. There's a scientific fact, unavoidable. There's a human need, unavoidable. And we need technology to bridge that gap. So in general terms, this is what we really do here at Princeton in the engineering school. And we're lucky because we're in a great liberal arts university. We're able to work with colleagues in the sciences, in the humanities, policy experts, and others to work on problems of this nature. We can look to solve social problems with technological innovation. Just an example, the very recent initiative in the School of Engineering is the Andlinger Center for Energy and the Environment, which was recently founded with a $100 million donation from one of our alumni, Gary Andlinger. The Andlinger Center is about technological innovation to develop sustainable energy sources, so it's exactly about this issue. But it also involves not only engineers, but also involves our colleagues in the Woodrow Wilson School, the Policy School, in the Princeton Environmental Institute, life scientists and geoscientists and so forth. So this is a good example of the kind of problem that we're working on here in the engineering school. And if you look at all the other talks in this series, you'll notice that they all have this sort of element of issues that combine technology with some kind of social need. Energy, tonight's lecture, sustainability, communications, transportation, health, financial security. That's also an engineering problem. You might not think so. And all but one of the speakers is affiliated with the engineering school. So in the course of this series, you're going to hear what we're doing, or a lot of what we're doing. So I don't really think I need to elaborate further in detail, and also I've run out of time, so I won't elaborate further. But I'm looking forward to this series. Thank you again, Nancy, and I hope you enjoy it. Thank you.
Sounds pretty good, doesn't it? And to get this series started, we have Professor Emily Carter. Professor Carter is Walter Marks 19 Professor in the Department of Mechanical and Aerospace Engineering in the Program in Applied and Computational Mathematics. She's also an associated faculty member in the Princeton Institute for Computational Science and Engineering, Chemistry Department, Chemical Engineering, and the Princeton Institute for the Science and Technology of Materials. I'm not even going to try to describe anything specific about her work. She's a theorist who seems to be comfortable in several fields, merging chemistry, quantum mechanics, applied mathematics, and solid-state physics. Professor Carter received her bachelor's degree in chemistry from UC Berkeley and her PhD in chemistry from Caltech. After 16 years at UCLA, she came to Princeton in 2004. She's the author of over 200 publications and is a member or fellow or has received awards from numerous organizations, including the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Association for the Advancement of Science. A theorist with an interest in applying theory to practical problems, Professor Carter seems just the person to open our series by sharing with us new ideas for green energy solutions. Emily.
Well, thank you very much, both to the organizers of this series, and it's a delight to be here to talk with you. And I also want to thank you for coming out tonight. You're all brave souls. Hopefully we'll all get home okay. So let me wake up my computer, who fell asleep while we're waiting here.
Is that tomorrow?
Let's hope not. This is Siberia, actually. So it's a beautiful photograph, I think, but quite apropos for tonight. Okay. Let's see. Right. So it's clear today that many of us are worried about the economy. But as Dean Poor so eloquently put it, that's one huge problem we have, but a much more long-lasting problem. I guess I have faith in the American economy and the global economy that it will come back. I have much less faith in this problem. This is a really serious problem for the 21st century, and that is that this is just showing, it's a nice, colorful picture that shows how energy is developed, the supply of energy that we have in this country, and how it's used, on the other hand, in terms of demand. And actually, Dean Poor already mentioned this. Our big problem is that 85% of the energy that we currently utilize in the United States comes from non-renewable fossil fuels. And you know, this is nothing new to any of you in the audience. I'm sure that you're aware of this problem. And I personally feel that it's unequivocal that it's contributing to global warming. Again, there are scientific facts. There are people that try to distort the scientific facts, but those scientific facts remain. And the fact that we get so much of our energy from non-renewable fossil fuels means that our foreign policy is also affected by it, obviously, because we need to have a source of oil and natural gas that doesn't just come from our own country. And it's clear that it has the ability to damage our economy. And so a couple of years ago, I decided to move, I consciously made a decision to try to move most of my research into trying to come up with solutions for the problems we face in energy. And so the title of the talk was New Ideas for Green Energy Solutions. And as you can see, it says here from computer simulations. And I'm going to try to convince you that actually a theorist like me has to work in tandem with experimentalists, of course, because ultimately anything that I evolve on the computer needs to be validated by an experiment. As I'm going to show you those, there are reasons, very important reasons, for actually doing computer simulations simply because the measurements can't be done. And so we have to find another way to get the information. And so what I'm going to show you is a potpourri of areas in which I'm working currently. Just, again, reorienting my research in the last couple of years. So one of them has to do with understanding how biofuels burn. Because one of the things we'd like to be able to do is have a renewable source of liquid transportation fuels. It isn't just a matter of generating electricity. There's going to be a need for liquid transportation fuels, at least for airplanes, for the foreseeable future. Okay? And so as a result, I mean, even if you have electric cars, I think it's very unlikely we're going to be able to have electric airplanes. Speak up louder. Sure. Thank you for saying so. I appreciate it very much. I always tell students that the people sitting in the back, their job, you see, you're doing your job. Your job is to tell me if you can't hear me. Is it better now? Because a little bit? I can speak even louder. Okay, I will. Okay, so we actually have a new center here that's led by Princeton University, that's funded by the Department of Energy, to understand how biofuels burn. So these are fuels derived from plants. And it turns out that we don't understand very well how they burn. And this is something that I and other colleagues of mine in the Mechanical and Aerospace Engineering Department are working on. But I won't talk about that tonight in detail. I will talk briefly about a long-standing project that's actually coming to an end in my group that I've been doing for the Air Force, which is to look at materials problems associated with jet engines. And so, of course, it's understandable why they would care about it. But from the point of view of energy, it's not just efficient airplanes, but also the same jet engines that are used on aircraft are used in power plants to generate electricity. So the same issues that arise in terms of how you make these these engines as efficient as possible arise for both airplanes and for power plants. And so I'll spend a couple of slides talking about some juicy details about that work. I've had a small project, just started some work looking at some of the materials issues associated with the reactor walls that are being designed for the fusion reactor, the experimental fusion reactor that's going up in Europe. Clearly, if we can get fusion to work, and basically a lot of the aspects of what goes on in the plasma of fusion are really well understood, but a lot of the issues associated with how you contain that plasma are not in terms of the kinds of materials that will be able to withstand the conditions that the plasma presents are not well worked out. And so that's something that I've done a little bit of work on, and I'll tell you, I think I have one slide on that. Another area is related, again, to energy insofar as we're talking about energy efficiency from the point of view of lightening the weight of vehicles. And so one of the things that I've done in the last 15 years or so is to develop a powerful computer simulation technique that allows us to look at the mechanical properties associated with forming parts of cars from lightweight metal alloys that could eventually be used to replace heavier metals that are used in vehicles such that you would improve the fuel efficiency. So I'll have a little bit to say about that. I'm not going to talk about this, but another project that's just started is to deal with some materials issues associated with what are called solid oxide fuel cells, which is another way of generating electricity from a liquid or a gaseous fuel in a clean way. And so there's a project that we've started this year on that. The other area that I have now started quite a big effort in is related to solar energy conversion. And so this is just a picture of one of the state-of-the-art solar cells, or what are called photovoltaics, photo being light, voltaics having to do with generating electricity. And so I'll talk about what are the essential issues in terms of developing new materials for photovoltaics, for converting sunlight to electricity. And finally, another area that we're working in is how we can actually develop materials, in particular what are called photocatalysts, that take in sunlight and actually do chemistry to, for example, split water into hydrogen and oxygen to have hydrogen as a clean burning fuel, or as something that can be used to generate another kind of fuel, a liquid fuel. And so I'll have something to say about that if you're willing to put up with me that long. Okay, so I want to justify for you why one should consider doing computer simulations. The problem is that, laboratory measurements, if you can do them, you absolutely should do them. But the problem is you get an incomplete picture of what's going on. You're limited by however you probe the material by whatever window it is you're looking through. And so as a result, what you end up often doing, for example, this is a picture of the materials involved in those jet engine components that I mentioned before. And what you're seeing is a cross-section of a bunch of materials that's actually, it's like an autopsy. Okay, so it's a post-mortem experiment that is done to look at what's happened after violence has been done to the engine. Okay, and that's essentially the way most materials characterization is done. And so the problem is you really want to see what's happening while it's happening, because a lot happens before you can look at it after the fact. So that's the main reason. The other issue, this is an example again of combustion of a flame, is that typically what experiments can see are just actually the stable chemical species that exist in that flame. They have a hard time seeing anything that involves an intermediate between different stable chemical species, and yet those could be very important in trying to understand what happens and to tailor the fuel so that it's burned most efficiently. So that's why you have to go beyond just experiments. Experiments are important, but computer simulations offer this tantalizing possibility to fill gaps in our knowledge. And so that's how I justify my existence. And also, it turns out that because you can work in tandem with experiments, you can offer interpretations of the experiments. You can actually go and make calculations on the computer that, if they're accurate enough, can be compared directly to an experimental observable. And it's a way to validate the computer simulations and also to help offer interpretations of the data. And then to be creative, to suggest new target materials or new target fuels that might be looked at to the experimentalist is always fun. So how do we do these computer simulations? I mean, I can't just go and use Microsoft Word and run a computer simulation. What I have to do is write down the essential equations that govern how how matter behaves. So I have to think about the physics that's involved and then be able to write some mathematical equations. And it turns out that for the kinds of systems that I'm interested in, the molecules and the materials, it's very hard. We don't know enough to be able to just write down a beautiful little equation that explains it all. We have to actually go back to the very basic physical laws. And those basic physical laws, in fact, are quantum mechanics. They start from the very basic understanding of atoms and inside atoms, the electrons, and how the electrons interact with each other and how they interact with nuclei. And so I say here independence is crucial because there are ways to do computer simulations where you sort of do a lot of tweaking and fit to experiment, and I don't like to do that. I think that's cheating. So what I want to do is to start just with the basic physical laws, pretend I don't even know that there was an experiment, and basically run my own computer experiment that I'm going to learn from and then compare to a laboratory experiment. And the way I'm going to do that, I need to understand how the electrons are distributed in matter. That turns out to control all of the behavior of molecules and materials. And so in order to be able to predict that electron distribution, I have to use quantum mechanics. So gives me the correct equations that describe that electron distribution. Okay, so I'm going to just summarize in a couple of slides some work that we actually did over a dozen years. Okay, so this is only just a few little bits of it. But what we were worrying about is the coating that is put on jet turbine engine blades. It turns out that, and I'm not trying to scare you, but it turns out that jet engines that are on an aircraft actually operate above the melting point of the blade. So that's above the melting point of the metal from which the blade is made. Okay, so that should really okay, you can be scared by that. But the fact is, it's a modern engineering marvel, right? Because what engineers figured out a long time ago, decades ago, is that if you coat the metal with a ceramic coating, okay, and it's not so trivial because there's it's a complicated. This is the ceramic coating. It's made out of zirconia. But then it turns out you can't just put the zirconia directly onto the metal. You've got to put another metal alloy on it. It's just, there's a lot of stuff here. It's a really complicated system. But the fact is that they work really well. But of course, one can always want them to work better, to work at higher temperatures, for example, to make them more robust so they can operate at higher temperatures to more cleanly burn the fuel. That would be the goal. That was the goal of our work, to get better fuel efficiency for airplanes and power plants. So it turns out that the current coatings that exist, that General Electric, for example, or Pratt & Whitney put on the engines that are in power plants and aircraft, they fail after a whole bunch of times of turning the engine on and off. Okay, that's what high temperature cycling means. And they fail at a particular interface between a metal alloy and an oxide, which is called a thermally grown oxide, this TGO. And so all that means is that under the operating conditions of the engine, an oxide grows in. This is actually what it is alumina. It's Al2O3 that grows in. And it turns out that once it gets too thick, then there's a mismatch between the metal and the oxide that essentially makes the whole coating come off. And of course, you'd like to not be in the air when that happens. I'm not trying to scare you. Okay, so it turns out also what clever engineers have figured out is that if you add these particular rather exotic elements, transition metals, to the alloy, this so-called nickel aluminide bond coat, it turns out it helps. The ceramic coating stays on longer, but it was really unclear until we did our work as to why that was. And so we were able to figure out why those particular elements, were so crucial in terms of improving the stability of the ceramic coatings. And because we could go in and interrogate how they helped stabilize this coating. We were able to understand fundamentally what was special about those elements, and that has led to design insights that essentially allowed us to suggest a new composition for this alloy that should allow one to get to higher temperature operation, and we have a patent pending on that. Okay? So the idea then is that what will happen, hopefully, is that this particular invention will help lead to more efficient planes and electricity production. So I'm thinking that I should skip this, but maybe I'll go through it. I'm just worried about time. But so this is a little bit of detail, just to give you an idea of the kinds of things that we look at. So it turns out, this is telling you about the role that hafnium, this is a really pretty rare element, so it's added in a small amount to this metal alloy, which is shown here, and this is that oxide that's growing in. And it turns out that hafnium acts like a glue. And it loves oxygen so much that it just sucks up to the alumina oxygens and essentially improves the so-called adhesion of the ceramic to the metal. And that's one role that hafnium plays. So what we learned from that is that it's really important to think about, okay, what kinds of elements really love oxygen? Because they actually may help stabilize the coating. We also found out that when the alumina grows, it turns out it makes polycrystals. And what a polycrystal means is you have a bunch of crystals that are coming together, they don't quite fit, and they have a bunch of room between them that are called grain boundaries. There are grains and there's a boundary between them. And this is an example of a grain boundary in alumina, aluminum oxide. And what I'm showing here is a cross-section of that grain boundary. And what we were able to discover is that another thing that hafnium and yttrium can do is to block transport of aluminum in the alumina to slow down the growth, and something called creep that I don't have time to talk about. But it's something which, again, leads to failure. So the idea is that what the hafnium and yttrium do, they're these big lumbering metal atoms that essentially sit in sites that frustrate the aluminum so that the aluminum can't go through the alumina to make more oxide. And so it stops the growth. And that's also really important. We also showed that yttrium, for example, and actually hafnium does it too, this is showing an energy as a function of moving, of sliding this grain with respect to this grain. And what we showed is if you don't have yttrium around, you have a certain profile shown in black, and it turns out that you can essentially double the barrier to sliding by just adding a little bit of yttrium at this interface. And we know that yttrium actually does get to this interface from experiments. So this is, again, a way in which we tie what we do to experimental work. We then looked at, this is another thing we can do on the computer. We could go through and basically look at most of the periodic table and of elements that we thought really love oxygen and figure out which one is the best one to add that would help slow down this growth. And we discovered that barium, which is a very big metal atom, which loves oxygen, increases this barrier the most, this barrier to sliding, which ends up leading to failure. And so that's the new additive that we've proposed in this patent to add to this metal coating. And so hopefully this will be a way to improve some of the efficiency of airplanes. Okay, so now moving on to this fusion example that I mentioned. So it turns out that nuclear reactors and fusion reactors, of course, they have walls, and there's all sorts of nasty stuff going on inside with particles, like neutrons, like high energy isotopes, radioactive isotopes, like in this case tritium and deuterium. And the material that forms the wall of the reactor has to be able to withstand some level of bombardment by those particles. And so it turns out that tungsten is being considered for part of to be used as a material for part of the components inside this fusion reactor. And you can sort of understand why tungsten might be a good choice. Tungsten is the metal that makes up the filament in the very inefficient incandescent light bulbs. okay? But it can exist at very high temperatures without falling apart, which is why eventually it falls apart. That's why you get burnout. But it lasts a long time. And so it can withstand very high temperatures. It turns out it can absorb neutrons well, and it has very high thermal conductivity so that it can wick away the heat as needed. But one thing that wasn't really known is how hydrogen and its isotopes, deuterium and tritium, that are formed in the fusion plasma, how they interact with tungsten. And so we undertook a study of this. And we took advantage of the knowledge that this tungsten plate is going to be bombarded with neutrons. And we know that one thing neutrons do is that they produce something called a vacancy. They produce defects in the material. The vacancy just means the absence of an atom, so it knocks an atom out of place. And what we showed is that the hydrogen isotopes in a perfect crystal of tungsten absolutely don't want to go into tungsten. So that's really great because you really don't want these radioactive isotopes to get embedded inside the metal for various reasons. You don't want the reactor wall to become permanently radioactive. That's a big problem. It also turns out that hydrogen tends to embrittle metals. And as a result of that, you could end up with, basically cracking of the whole instrument. So that would be a big problem. But it turns out that in the presence of vacancies, hydrogen and its isotopes love these vacancies, and they go and they collect at these vacancies. And so what happens is, if you need something,
I think your well water mic is dead.
You think it's dead?
Yeah. In other words, you move much more furiously, you sound off. Yeah. Stop. I think that's true.
The battery is dead.
Yeah.
If you can use that mic, because there aren't any more batteries.
Okay. Well, then I don't need it anymore. Can you hear me in the back? Can you hear me better this way? Okay, so now I have to do this. Okay, that's all right. So anyway, the hydrogen, what we have shown is that these isotopes of hydrogen will in fact bind strongly to vacancies and in tungsten. And as a result, we were also able to look at the embrittlement. You can't read this, but this is basically showing the stability of the tungsten as a function of how much hydrogen is there. And when it goes below zero, it's not stable anymore. And so the point is that the hydrogen in the presence of neutrons is going to want to get into tungsten. So there will be important issues associated with how you might alloy the tungsten or anneal the tungsten, heat it up to get rid of those vacancies, to essentially inhibit the formation of the vacancies so that you can inhibit the incorporation of these hydrogen isotopes. And it turns out we took that that suggestion didn't come out of thin air in terms of how we think you could potentially solve the problems that tungsten will face. It had to do with work that we completed recently having to do with looking at how to protect steel from hydrogen and also steel from carbon incorporation. So steel is basically just iron, Fe, okay? And so we did a lot of work related to protecting steel, thinking about the interaction of how basically the energy and the rates of how fast carbon and hydrogen can get into steel, and they can cause all sorts of problems as shown here. Basically, you make compounds that can then decompose and just form all sorts of messes. And the hydrogen essentially, as I said, embrittles the steel and makes cracks. And so one question we wanted to answer is, could we design an alloy that would inhibit the hydrogen and carbon from getting in? And so what we did is to, again, look at our friend, the periodic table, and figure out, okay, are there iron alloys that could possibly withstand very high temperatures and that could, in fact, be useful for this purpose? And there were two that were important. It turns out that iron aluminide and iron silicide have very high melting points. They also both form stable oxides on their surface in such a way that they don't corrode. Okay, that's of course very important as well. And so what we did was to investigate how hydrogen and carbon might get into these and compare them to how they behave going into steel itself. And don't worry about the units here, just think about the numbers. What these are an indication of the energy, the amount of energy you have to put in to dissolve hydrogen. This is showing a hydrogen right here. It likes to sit in tetrahedra, actually, of metal atoms. And this is the amount of energy. It's uphill, actually, to put hydrogen into iron aluminide, and even more uphill to put carbon into, here's the carbon shown in gray. It likes to sit in this other kind of site surrounded by 6 metal atoms, and it's even more uphill. But it turns out if you go to iron silicide, you find that the amount of energy that it takes to put hydrogen or carbon into iron silicide is much, much higher than for iron aluminide or for iron itself. And so it's actually 2 to 4 times more unfavorable to put carbon and hydrogen into iron silicide. And so one of the things, then into steel itself, and so one of the things we've suggested is that if you put a thin film of this iron silicide on steel, this would help actually protect the steel from hydrogen and carbon incorporation. Okay. That sounds like it's on. Feedback. Okay, can you hear me? Okay. Hopefully I don't have to start over. You heard everything, right? You're going to tell me you heard everything. Okay, so I want to switch gears yet again and just give you this. The whole talk is to give you a flavor of the different kinds of things that we can do now with computer simulations. And that is to start thinking about designing lightweight metal alloys that can be used to replace steel components, for example, in cars, so that you lighten the weight of the car and improve its fuel efficiency in that way. So the question is, what to focus on, okay? How do we choose the alloy? Well, the thing that it turns out to be most important are the mechanical properties of the alloy. So we want to be able to, for example, make sure that the alloy is ductile enough, bendable enough, deformable enough that we can make components in whatever shape we want. But we don't want it to be so ductile that it just crumples horribly in a crash, right? It's got to be that it has enough strength to be crash-worthy, for example. So it turns out that ductility and strength, they work in opposite directions, and there's always going to be a trade-off. One has to look at the mechanical properties and try to optimize something in between. And that's a real challenge. It also turns out that these properties are controlled by something called the microstructure, so something that's sort of on the micron scale or actually even below. Micron is 1/1000th of a meter. Okay, so something you could see with a microscope or at a scale even below that. And so it's controlled by those grain boundaries, like the thing I showed you for the aluminum oxide, so where 2 different crystallites come together, as well as this weird thing that you've probably never heard of called dislocations. I'm going to show you a picture of them. It's a defect in a crystal. Okay, so a crystal has all the atoms arranged very nicely, in a regular array. But a dislocation basically messes up that regular array, as I'll show you in a moment. But all of these mechanical properties are controlled by these weird defects. And so here is an example of it's a cartoon of a dislocation. So here I've got that crystal shows this regular array. And now what happens is, suppose I try to push on part of it. I try to deform the crystal. What you see is that when I deform it, I create this weird little defect that wanders through the material. That defect is called a dislocation. This one is actually what's called an edge dislocation. And what's really amazing is that the material essentially is able to deform much more easily by just carrying that defect through, instead of just sliding the whole thing, the whole top of the crystal across. That costs a tremendous amount of energy because a bunch of bonds have to break. In this case, what you see is that a whole bunch of the crystal is totally undeformed, and over here it recovers and is undeformed. But what happens is just around that dislocation, the material is sort of messed up, okay? And how those guys form and their structure actually determines these mechanical properties. And so we're very interested in in being able to predict these things. And again, I'm going to criticize experiments. I mean, they're very important, but they are really autopsies, okay? They're looking post-mortem after you've deformed the material. You take a slice of it, you stick it in an electron microscope, and you ask, what do you see? The problem is that all the fun stuff happened during the deformation. And you want to be able to look at that, and the only way to do that at this point is with computer simulations. And so it turns out that the simulations that have been done to date have all been what I would call cheating simulations, okay? Because they take information from experiment in their modeling. And what we've done now is to create this very powerful quantum mechanics computer code that can allow us to, again, not take any information from experiment, but it is accurate and allows us to treat enough atoms to describe, that was exciting. No, I think it's okay. To treat enough atoms that we can actually look at these kinds of defects in crystals. So I know this probably doesn't mean much to you, but the point is that quantum mechanics codes typically can treat about 100 atoms, roughly 100 atoms. And one thing we've been able to do is to extend the range of applicability for these kinds of materials so that we have actually shown you could treat up to 1 million atoms with quantum mechanics, which has never been done before. So that's kind of exciting. You don't actually, for a lot of these problems, need to treat 1 million atoms, but 20,000 atoms actually is a useful number, which has not been possible with quantum mechanics before our work. So that's what we're doing, is we're predicting how these dislocations basically give birth, how they come to be, and what their structure is, and how they move. And this is, you probably can't see very well, but this is actually telling you something about the internal structure is about on the order of a nanometer, okay, which is a billionth of a meter, okay, and so what we've been able to do is predict for aluminum in this case what the internal structure of that dislocation looks like, and we've been able to look at what happens when it moves. This is another simulation that is looking at actually a larger length scale, so it's actually looking on the micron scale, looking at how, as I deform aluminum, so there's a deformation coming in here, something's pressing on it, and these little cartoon things that look like perpendicular signs are meaning this little edge dislocation is forming. And this is 4 different simulations, one in pure aluminum showing what happens in terms of the dislocations that form. And this is one that has, these 3 have magnesium atoms that have replaced aluminum atoms in the lattice. And what we've been able to learn is how the dislocations, both the birth of the dislocations and their movement, are affected by the magnesium atoms and how they're distributed in the aluminum. And so what we're doing is working to design aluminum and magnesium alloys by looking at other additives, other elements as well, and also playing with the microstructure to see if we can optimize the strength and ductility in order to manufacture lightweight efficient vehicles, energy efficient vehicles. Okay, so I'm going to come to my last topic, which is about solar energy conversion. And the idea is that sunlight, which has a tremendous amount of energy in it, most of it's wasted, okay? It shines on the planet, and we just don't use it, okay? Well, plants use it. They, of course, use it in photosynthesis. But the holy grail is if we can come up with a cheap material, that's really critical, a cheap material that can take in sunlight and voila, convert it to electricity or to fuels that can be used for transportation. So I mentioned already, I showed you this picture already, that this is sort of a state-of-the-art design for photovoltaics. And the problems are, you'd like to improve the efficiency further. These particular ones are pretty efficient, but they're incredibly expensive, so they're never going to be deployed widely. they tend to be made of elements that are toxic. And so you'd really like to be using things that are earth abundant, using elements that are earth abundant if possible, and so that they would be cheaper. So one of the things we've been doing is thinking, just trying to think outside the box and think about new materials. And what we've done is to take some cues from nature. And so what I'm going to tell you about are, these are little interior structures of enzymes that show that certain elements, in particular, again, actually transition metals. We talked about transition metals earlier in the metal oxide thermal barrier coating problem. And it turns out that certain transition metals are used by enzymes to take in light and eventually make food for the plant. Okay? So, or also to do things like form hydrogen, or to reduce carbon dioxide, okay? Or to split water, to do all the things that we humans are not intelligent enough to figure out how to do. Okay, so what are the key issues? So just briefly, so the key actors are electrons. We basically want to convert the sunlight, we want to put all the energy of sunlight into the electrons in materials to get them to absorb that and be at a higher energy that then can be converted into electricity or to fuel. Okay, that's the general idea. And the thing to know about electrons is that they're both distributed in space. They're spread out over space, but they also are distributed in energy. And they have a particular kind of distribution in energy that I'm showing here. So this is low energy, high energy. And just like I'm sure you learned about atoms having core electrons and valence electrons, well, in a material, there's also a set of core energy levels and valence energy levels that are full of electrons at low temperature. That's where all the electrons live, at low temperature. But and then there's a whole bunch of states that are called conduction states. So this is called the valence band. This is called the conduction band. These are empty at low temperature. And the sunlight gets used to take the electrons from here and populate these states for further use. That's what we're going to see. And a key feature that is determined by whichever materials you use is the so-called band gap between the valence, the occupied states, and these unoccupied states that are called the conduction band states. And so the idea is that we want to take the sunlight, we excite the electrons to this set of energies where the electrons are very loosely bound, and that's why it's called the conduction band, because electrons can conduct through the material just like in a metal. In a metal, the electrons are not strongly held by the nuclei either. And the idea then is to harvest electricity or to catalyze chemistry, these chemical reactions that we're interested in. So another key concept, so the key actors are electrons. The key concept is conservation of energy. The energy can't disappear. So what we're trying to do is take the photon energy, that's the bundle of energy from sunlight, and convert it. So here I've got an electron that lives down here, and the sunlight is going to come in and excite the electron up to this conduction band, and it leaves behind what's called a hole. The hole is just an absence of an electron, okay? And that hole, one can design the material in such a way that the electron and the hole move in opposite directions. And we'll see how that's key to how a solar cell operates. But another really key feature is that the only light that's absorbed is light that has energy above the band gap. And that also then plays into the efficiency of solar cells. So how does a solar cell work? Again, you have the same kind of picture. You have a valence band electron that gets excited by this photon, creates a hole here and an electron up here. So there's the absence of an electron at this energy and the appearance of an electron at this energy. And that creates a current, this current I out. Then the electrons flow to the external circuit. In this case, it lights up a light bulb. Okay? The hole goes in the opposite direction. They recombine to complete the circuit. And that's the way the solar cell operates in its essence. The power power that you get out of a solar cell is given by the product of the voltage, the output voltage, and the current. Now, it turns out that the output voltage is limited by that material property, that band gap. So once again, we have to worry about what material we use, because it puts an upper limit on the power we get out. And so the idea is you have to, again, life is full of trade-offs, and here's another trade-off. You want maximum generation of these electrons and holes and separation to get a maximum current out. But you'd also like to do that at maximum voltage. And it turns out those work in opposite directions, as we'll see in a moment. So the solar cells that you may have on your roof or that you have seen are invariably made out of silicon. Silicon is the most abundant, well, it's one of the most abundant elements in the Earth's crust. And so in principle, it's cheap. The problem is that in the Earth's crust, it comes as an oxide. And so in the process of making it ultra pure as it needs to be to get very large amounts of current out, otherwise things go wrong, as I'll explain in a moment. Well, that process costs a tremendous amount of energy and money. And so, and the other problem is it actually doesn't have quite the optimal band gap. It's close, but it's off a little bit. So you could, in fact, have higher power if you had a higher band gap than you have in silicon, which would be better. But the problem is that, you know, the processing of silicon is such that it really increases the cost. And the efficiency is not as good as we would like. Okay, we've really nearly tapped out the efficiency in silicon solar cells, so we're going to have to look elsewhere. So as I mentioned, what we've been doing is trying to take cues from nature about where to look. And so what we did was to think about, well, how does nature separate charge? Remember I said we have to separate the electrons and holes from one another. How does it transport charge? How does it transport electrons? And how does it make fuels? And the really interesting thing is that if you go and look at what nature does, plants, algae, and bacteria, and the enzymes in them, what they do is they use only metal oxides and metal sulfides, and very particular metals. And these are some examples. You can see here Fe again, iron, just like we saw before, is one of the ones that's used. And so our strategy is not to, you know, harness the plant itself, because the plant has to do a lot of things in order to stay alive that actually reduce its efficiency dramatically. So what you'd like to do is to make an inorganic substance, a substance that is not alive, that doesn't have to spend energy keeping itself alive, but does the same thing. And so what we did is to suggest that one look at these particular metals, and in particular also to focus on metal oxides rather than the metal sulfides. The reason that these, I don't have time, I can tell you later. We'll talk about all of this in much more detail. Anyway, these are the elements that show up in these plants and algae and bacteria. There aren't very many of them. They occur over and over and over again. And they're earth abundant. They're cheap. And our idea is to use them in their cheapest form, oxides. These also happen to be good because they don't corrode. And then the issue is to think about these oxides. These are two examples of oxides we're working on. One is copper oxide, the other is manganese oxide. And we want to optimize the composition as well as the structure at this nanoscale, because we can look at that level and make changes in order to optimize the properties. The question is what to optimize. So then I have to go back to the physical properties. And the issue is that band gap. And also, we have another problem that has to do with what's called electron-hole pair recombination. And I'll mention that in a second. So the first issue of the band gap. So here's, again, this valence band and the conduction band, energy going this way. I have an electron here, and it turns out that if I have a photon that's shown by the squiggly arrow that has energy large enough to cross that's above the band gap, I can get an excitation, and I can use this excited electron to do whatever I want with it. But if If I have a photon that has much less energy, like shown here, that has an energy, the length of the arrow being less than the length of this arrow, then it just doesn't get absorbed. So there's whole parts of the solar spectrum that don't get absorbed because if the band gap is too large. And so you'd immediately say, well, of course, then I want to use a small band gap, because if I use a small band gap, I can harvest most of the sunlight, and that would maximize the current. But if I use a small band gap, I put very hard limits on the voltage I get out. So I really want to use a large band gap because that maximizes the voltage. So here's the trade-off. You have to have a trade-off of an intermediate band gap. And so we want to do band gap engineering to be able to come up with the optimal band gap. In addition, there's this problem that here I've got the electron and hole, and a photon comes in, the electron gets excited up to here, and then the problem is that the electron could change its mind, okay? It doesn't really have a mind, but it doesn't, because it's excited, it can just as easily decide to come back down in energy and give up that energy as heat, which is a waste. And that often happens, and so this electron-hole recombination is something we want to stop. We want to have ways of tricking the material into not allowing those electron-hole recombinations, because if they happen, then we've just lost all the energy that we were trying to harvest, because we won't get the current out, and we won't be able to do chemistry with it either. So here are some materials design strategies. I'm going to show you one example that I'm excited about, where we seem to have, I think, a success. And that has to do, so in terms of maximizing the power, as I said, we have to use an intermediate band gap. And so the question is how to optimize that band gap. And what I'm going to show you is that we can actually tailor the band gap by alloying oxides together. We also want to avoid recombination by essentially maximizing the electron-hole pair lifetime. So here's a hole, here's an electron, and I want to make sure they live long enough that they can separate. If the lifetime is too short, they'll just recombine. And so that turns out to be actually a quantum mechanical property, an intrinsic thing that I can calculate from quantum mechanics. And we have some, I think, very cool ideas about how to design these oxides that will exploit the spin of the electron in various ways that will prevent this recombination. So I won't tell you the details about that, however. Okay, so the last thing I mentioned was photocatalysts. And it turns out that what's really interesting about solar energy conversion is this idea about having a catalyst that can make a fuel. The physical processes involved for photovoltaics or photocatalysts are identical at the beginning. Absorption of light, separation of the electron and hole, excitation of the electron, and separation of the electron and hole. And then instead of making a current, we're going to use the electron to reduce something, to do a chemical conversion, and we're going to use the hole to oxidize something, to do another chemical conversion. So here's a cartoon showing you idealized photocatalyst particle. I have a sunlight that appeared, a little photon came in here, and it generated this electron-hole pair, and then they separate to either side of a particle, and then they do some chemistry, maybe converting water to oxygen and water to hydrogen. Okay? It's been done, just not very efficiently. What are the key things? It turns out that photocatalysts are even more challenging. It's why we don't have effective photocatalysts yet. Because here's that valence band and conduction band again. Now I have other constraints associated with the chemistry of taking water to hydrogen and oxygen, and it's shown here in terms of the reactions. It doesn't matter. The point is that basically the energy constraints make it so that I have to place these energy levels that I've shown here, the conduction band and the valence band, they have to sit outside of these lines. Okay? It just places a constraint that means the material has to do even more than I was saying it had to do when it's a photovoltaic. And so that's what this says here. And it turns out that in order to, for example, split water or to reduce carbon dioxide, which is another thing one would really like to do, is it's terrible we have all this CO2 in the air, and wouldn't it be nice to actually use it for something useful to generate fuels? So we need to be able to reduce the carbon dioxide to a fuel. And it turns out that all of the thermodynamics, the energy constraints, tell us that we have to have, it places bounds on this energy gap and tells us that we have to use visible or ultraviolet light absorbing materials. And of course, you'd like to use visible light because the solar spectrum, the way the light is distributed from the sun, of course, when you look with your eyes, what do you see when you look at the sun? Well, you're not supposed to do that, but you see yellow light, right? And so you'd like to have something that has a band gap that's somewhere around yellow, that corresponds to the energy of yellow light. And that's what's meant by this visible light absorber for maximum absorption, because that's where most of the photons are. So, as I said, right now the best catalyst is just at most a few percent efficient, and it also requires additives, so it kind of has to cheat. So we're working on this idea of trying to design metal alloy catalysts with all of the issues involved that I won't get into, okay? But this is the future. This is something which I'm very excited about, and that I really think we will be able to make progress on in the next few years. I'm going to give you one result that I'm very excited as a preliminary result, having to do with tailoring this photocatalyst material. So we started looking at nickel oxide. Nickel was one of the elements that exists in plants and bacteria and algae. And it turns out that the conduction band minimum, that's that edge of the conduction band, turns out that it's perfectly placed so that you could reduce water to hydrogen, which would be great, okay? And it's known that it, in fact, can do that. And the cool thing is that it's cheap. It also doesn't suffer from what are called, chemists hate this, back reactions. Platinum, which is the usual thing that's used to reduce water, for example, to split water with an electrolyzer, for example. Platinum is very, very expensive. And so this offers an alternative that could be more efficient. The other cool thing is that the nickel atoms in this crystal are made up of what's called nickel 2+. It means that they have 2 electrons that have been stripped out of the atom. And it's extremely important that this guy is very stable. It doesn't like to either lose an electron or gain an electron very easily. And it means that it won't trap electrons or holes. And so it should be expected to exhibit pretty good conductivity, which is what we need. We need the electrons to be able to get through the material so they can go somewhere to reduce water or reduce carbon dioxide. So that's the good news. The bad news is that the band gap is way too big. The only thing it will absorb is UV light or above. That's a problem because if you look at, that means it only uses a couple % of the solar spectrum. So immediately we have something which will at maximum be a couple % efficient. So that's just totally unacceptable. So we have to think about then how to potentially do band gap engineering by alloying the material to bring the gap into the visible range. So we got the idea to think about alloying it with zinc. Okay, we'll talk later why, and what I'm showing you are raw data. Okay, so they're not very meaningful to you, I'm sure. But I just want to point out these 2 numbers here. This is a spectrum that we calculate showing what the energies are for electrons in nickel oxide, and this is in an alloy with zinc oxide. And these numbers are predictions of the band gap. And what you can see is that I can take pure nickel oxide and I can reduce the band gap by about 1/3. And that's all I need. This number is in the visible. It's almost the optimal band gap. So I find that very exciting. It means that we can think about making these alloys and now going to test them in the laboratory to see whether they in fact do become efficient photocatalysts. So I'm sorry, I think I should have stopped at 9, but this is my last slide. And this is just my dream, okay, that I wish for all of us, which is that at some point we will all of us have solar cells on our roofs. We will have photocatalysts that actually sit next to the solar cells. Why? Because I want those photocatalysts to generate either hydrogen or preferably a liquid fuel that at night could run a microturbine to generate electricity and to heat your house. Okay? So that you'd have something working in the daytime that was photovoltaics. You'd have something working at nighttime that came, again, still from solar energy and from water and carbon dioxide. And that you use the electricity to power a hybrid car that's made of my lightweight alloys. So thanks very much. I just want to acknowledge the different agencies that have funded the work, including Princeton University, which is not an agency. And I need to give thanks to the students and postdocs who've been, who've really made this work possible. So I'd be happy to answer questions.
How soon?
I can't answer that. I mean, I just hope that, I'll tell you something that I'm very hopeful, because for 30 years, we really have starved the investment in this area in terms of research and development. And basically starting a year ago, there was a new investment made. I hope it continues. There was a huge investment in 1973 when there was the last big oil crisis. We had a huge investment, for example, in solar energy. 2 years later, when the price of oil crashed, we stopped investing, and we fell asleep for 30 years. And so my hope is that we won't fall asleep again, because it requires a continuing investment, which is something that Germany and Japan have done. Almost all the work progress that's been made in photocatalysis has been done in Japan, because they've had a continuous investment in research and development. And so I haven't answered your question, because it won't happen without that investment, because we have to be able to really have a concerted effort. And it's very exciting, because the Department of Energy was given funding now to start very large efforts in these areas, okay? And not in almost every area I mentioned, okay, if not every area. And I firmly believe that, just like with the Manhattan Project, okay, if you put enough smart people working on a problem with different expertise, which is what they're doing and what we're doing, then the problems will get solved. On what time scale? I don't know. I'm sure we will see more efficient solar cells in the next few years, for sure. Okay, photocatalyst is harder.
Is this part of the technology that they're using for the desalination?
I don't know the answer to that. I mean, I don't know the answer to that, the current technology. Yes?
Is there enough solar energy, let's say, in terms of total power coming down in central New Jersey that covers an average house roof? Is there really enough power there with the limitations of the wavelengths of light to, say, meet the needs of a typical resident?
During the day. The problem, absolutely, during the day. But the problem is really, I mean, another issue that I haven't mentioned here that's really important is that we have very inefficient buildings, right? And so the more that we do in terms of the low-hanging fruit in energy and environmental protection is really improving, because we know how to do it, how to design better buildings that are more efficient, okay? But that's a separate issue. The real problem with solar energy right now, well, there are two problems. One is it's still too expensive, okay? The second problem is storage, okay? And that's why there are many ways in which people are looking at the storage problem. I happen to be thinking, let's use the photons to create a liquid fuel that then can be used later, okay? But other people are thinking about, and there are many avenues for how you store energy. But the problem is that right now, you have to get energy from the grid at night, because you don't have a means really of storing a lot of energy from your solar cells. Yes?
why you don't like the triple junction solar cells? You mentioned you're working on those other cells because you don't like the state-of-the-art solar cells.
No, I mean, yes. So why don't I like multiple junction solar cells? So what are multiple junction solar cells? I didn't discuss this. Basically, these are cells that have more than one material that are glued onto one another to absorb more light. I don't dislike them. I think ultimately we probably have to have an array that absorbs more different parts of the solar spectrum. I was just, dissing them because those are very expensive and are made of materials that, that you cannot envision deploying extremely widely, okay? So that was the only point there. There's nothing wrong with the design of multi-junction solar cells. They're fine. Well, because they tend to have cadmium, tellurium, selenium. They have, they tend to have elements that are toxic, yeah. Many of the most efficient ones, yeah.
This is something like your running gamma in your GAL plus.
Yeah, no, I agree with you. But again, they're not, I mean, you're not, okay, we could have a separate conversation about that. Yes?
So to model something like this, which has so many electrons, you need light for atomic potential. And how do you know that you've calculated the light potential?
So I don't calculate a potential, okay, so inner atomic potential implies I'm doing something classically. To me, that's what it implies. What we are doing is we're treating the problem fully quantum mechanically. So we derive the interactions of the electrons, both the core and the valence interactions, strictly from the quantum mechanical wave equation, the Schrodinger equation. Okay.
Using computation?
Yeah. 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 Yes.
With the situation right now, we have solar panels. Is there any way that the solar panel can retain heat to melt snow, or does it have to be wiped off mechanically?
That's a really good point. I mean, it is a problem. So if they're covered with snow, they're not going to work. So, that's also an issue. That's an issue for all solar cells. Is they tend, for example, where are most solar cells put? They're put in the deserts, right? But even those, you have to bring water in to clean them. Okay, so that's an important point. I should also mention, it's a subtle issue, but you don't want the solar cells to get heated up because they operate much less efficiently when you go to higher temperatures. Okay, but if they're covered with snow, it's not going to work.
Maybe one more.
Yes.
You mentioned improving the efficiency of gas turbines. What's your estimated efficiency?
I don't have an estimate. I mean, because it hasn't been validated. I mean, that's not something I calculated. Okay. What we did was to suggest a change in the materials design, and if I can get the engineers who actually make these things to incorporate it and then test it, I can give you an answer, but I can't otherwise, because it's such a complicated system that changing one thing, I can't tell, what that's going to do overall to the efficiency. All I'm able to say is that it should you can use it either to extend the lifetime by keeping it at the same temperature that you're operating it now, or you can run it at a higher temperature and have perhaps the same lifetime you have now. So how much more that improves the efficiency, I don't know the answer to.
Well, that's it.
Thank you so much. Well, complicated, you made it understandable.
The quantum mechanical wave equation, the Schrodinger equation.